Hey everyone, wish I could be there today, but unforeseen circumstances are not allowing me to be there. Hopefully, I'll be back tomorrow. So what I have is I made a video for you to kind of explain what I would have been teaching you in class. So hopefully, we had someone put it up on the big screen TV for us so everybody can watch and then get to work. Gonna start off with some review just about multiplying and dividing scientific notation because that's also going to be in the next study island assignment about computing with scientific notation. So I'm going to run through this part kind of quickly. When we're multiplying coefficients or multiplying scientific notation, first step, multiply those coefficients. So I'm looking at the 3.2 and the 4.8 and I multiply those together and I get 15.36. And right away, we should kind of be thinking, uh-oh, that's not good because that number is not in between 1 and 10. So we're going to have to address that a little bit later on. All right, so we multiplied the coefficients. Then the next thing we do is we add those exponents. All right, because we have that property of exponents, a to the m times a to the n. We add the exponents, m plus n. We keep the base the same. So we're going to do the same thing here. 10 to the 5th times 10 to the 7th, since they have the same bases. We simply add 5 plus 7 to get 12, and we keep that base. So it's times 10 to the 12th power. All right, so as mentioned, this is not between 1 and 10, so we need to address that because that's not scientific notation. But what we can consider is we can change this into scientific notation. We can move that decimal one spot over, get 1.536 times 10 to the first power because we moved it one spot. And then we still have times 10 to the 12th power. And we can go back and use that property that we just had where we add the exponents. So 1 plus 2 gives us 12. So this, in the end, will be 1.536 times 10 to the 13th power. All right, so real quick recap. When you're multiplying scientific notation, multiply the coefficients and add the exponents together, and if need be, adjust the coefficient. So now we got a happy coefficient. He's between 1 and 10. All right. Dividing is very, very similar. Very first thing we're going to do is divide those coefficients. So if I take 8.75 divided by 3.5, I get 2.5. All right, and that makes us happy because he's between 1 and 10. And then we subtract the exponents, 10 to the 18th divided by 10 to the 11th. Once again, we have that property. If we had a to the m over a to the n, we subtracted those exponents. It would equal, same base, we keep the a to the m minus n. So we're going to keep that 10 and just take 18 minus 11 and get 7. So this one would end up being 2.5 times 10 to the 7th. So dividing in scientific notation, divide the coefficients, subtract the exponents, and if need be, adjust the coefficient, but we didn't have to in this point. All right. And then just another quick review. Whenever you see E, some calculators make it E, some do 2 E's, but whenever you see E, that's literally just times 10. All right, that means, okay, we have scientific notation, and if you think about why they used E, they're basically saying, well, this is the exponent. 17 is the exponent for it. That's why they use E. So it's signifying, okay, we have scientific notation and the exponent is 17. All right. And we could put these in that old-fashioned calculator notation. If I had 2.5 times 10 to the 7th power, that would just be 2.5 E7. All right, meaning that the exponent is E. All right. I'm going to pause real quick so I can erase the board here. So the next part is adding and subtracting with scientific notation. I should have done some cool magic trick to make it just disappear and appear. Didn't think ahead like that. So we're going to start off very, very basic. All right, so this is in standard notation, obviously, not scientific notation, but I want to cover looking at this in standard notation so we kind of understand why we have to do the things we do in scientific notation. So going way back in the math time machine, back to elementary school, when you had to subtract numbers like this, the first step was making sure that we align the place values. We have to be able to add the ones place to the ones place, the tens to the tens, hundreds to hundreds, thousands to thousands, and so on and so forth. And a lot of times we did this vertically. All right, so I have the 27 million, and then I'm going to line up each of these with their corresponding place values. So ones with ones, tens with tens, hundreds, and so on and so forth. When you did this in elementary school, you might have even used kind of graph paper or had lines, representing all the different place values. And then we just go right to left and add everything up. 0, 0, 2, 4, 0, 0, 7, 2. So this one ends up being 27,004,200. All right. Key thing is lining up the place values. All right. Same thing with subtraction. All right. I got a subtraction problem here. And once again, they say line up the decimals, but lining up the decimals really means line up all the place values. All right. So I'm going to take this number, and like I said, I'm going to do it vertically again. I'm going to put them under. So I have 1, 2, 3. I got 4 zeros. 1, 2, 3, 4. Then I have that 5. And then subtracting it, same thing. 7 minus 5 is 2. 4 minus 0 is 4. And then I've got all of these zeros left. So the key thing here is making sure that we line up the place values. All right, if we don't line up the place values, we can't add and subtract the correct way. Now, with that in mind, remember in scientific notation, that's exactly what the exponent is telling us. It's telling us how far that decimal has moved. So if I take 5.7 times 10 to the 8th plus, say, 3.2 times 10 to the 6th power, all right, these exponents tell us how big these decimals are, or these numbers are. I think I changed my mind. I'm going to go ahead and make these the same exponent first. So they're both 8. So they're both equally big. All right. So what that means is the 3 and the 5, they are actually in the same place value. All right. The 2 and the 7, they're actually in the same place value. Remember, this means how far the decimal place moved. So if I took this number real quick and I wanted to put it into standard notation, 1, 2, 3, 4, 5, 6, 7, 8, and fill in the zeros, that's what this number would be. And if I did the same thing, 1, 2, 3, 4, 5, 6, 7, 8, that kind of shows you that these are in the same place value. So we can go ahead and add them together. All right, starting right to left, in case we need to carry things over. We don't need to. All right, so we get this number here. What is this? This is still in the millions, 890 million. Okay, now I want to show how this works in scientific notation. All right, because the exponents are the same, I know that I can just add these together. All right, I can take 5.7 plus 3.2 and get 8.9. And then it's really saying, okay, this is 570 million, this is 320 million, so now I have 890 million. All right, the same thing in scientific notation. All right, this matches our standard notation number. All right, so as long as the exponents are the same, you can just add the coefficients and keep this the same, because if we take thousands plus thousands, we get thousands. If we take hundreds times hundreds, we get hundreds. If we take millions times or plus millions, I think I said times for all those issues. It's adding, sorry. So if I take thousands plus thousands, I get thousands. Hundreds plus hundreds, I get hundreds. Millions plus millions, I get millions. All right, so that's what we're doing here. So just another quick example. Say I have 8.7 times 10 to the 3rd power. So 10 to the 3rd power, that's 1,000. So we're basically talking about we have thousands here. All right, now I'm going to subtract this time. I'm going to subtract 5.2 times 10 to the third power. So once again, I'm taking thousands minus thousands, so I'm going to get thousands back because these exponents are the same. So that means the 8 and the 5, they are in the same place. The 7 and the 2 are in the same place. So I can just subtract these. 7 minus 2 is 5. 8 minus 5 is 3. And since I'm taking thousands minus thousands, I get thousands back. So this is going to be 3.5 times 10 to the third power. All right, so now the big question, and this is kind of how I started. What happens when the exponents aren't the same? All right, so like that very beginning example, when we had like 27,000, and then we had just, 4,200, I think it was. All right, we had to line up the place values. Same thing with scientific notation. So if I have 4.2 times 10 to the 8th, and I want to add to that 2.3 times 10 to the 7th. All right, because the exponents are different, the 4 and the 2, they're not in the same place. All right, the 2 and the 3, they're not in the same place. So there's not a shortcut that we can do here where we can just add the coefficients and keep the exponents. All right, so you might ask, well, what do we do? All right, and the answer is, all right, let's take this out of scientific notation, all right, where the coefficient is between 1 and 10. Let's take it out of scientific notation so we can get an exponent of 10, or an exponent of 8. That's the same as the other one. All right, so the idea here is, okay, this is a big number, so we want to remember 3, 4, 5, 6, 7. So the decimal moved 7 spots to get between the 2 and the 3. Well, if we want to make it 8, we got to go 1 more spot. All right, so we're going to change this problem to 4.2 times 10 to the 8th plus 0.23 times 10 to the 8th. All right, so we adjust the coefficient and the exponent so we can match the exponents together. And now we can go back like we were doing before. We can add these exponents together, the coefficients together, lining up the place values like we did before. And because they're both times 10 to the 8th now, we can keep it times 10 to the 8th. All right, and I think that's 100 millions. All right, so we have 4.2 hundred millions plus 0.23 hundred millions. So we're going to get 100 millions back. So we just add these 3, 4, and 4. So these added together give us 4.43 times 10 to the 8th power. All right, I want to do a few more examples because this is obviously the new part of what we're looking at. I'm going to make the decimals a little bit farther apart. Let's go subtraction this time. All right, so let's go 8.9 times 10 to the 9th minus 7.3 times 10 to the, let's go to the 5th power. All right, so they're way far apart now. We're going to have to do some borrowing here. So once again, this is a very large number, all right, because the exponent is bigger than 5, or is bigger than 1. I'm sorry, because the exponent is positive, we know it's a big number, larger than 1. So originally, we moved 5 places to get between the 7 and the 3. Well, to get to the 9, we got to move 4 more places. 1, 2, 3, 4. So we're going to add 3 extra zeros here, all right, to make sure that we have times 10 to the 9th power. So this is going to change to 8.9 times 10 to the 9th minus 0.00073 times 10 to the 9th. We always want to match the larger exponents here. All right. Now we can do the subtraction. So we can put this in vertical form now, lining up the decimals. I'm actually going to need some extra space here. So minus 0.00073. And I'm going to go ahead and fill in the rest of the zeros there. So times 10 to the 9th times 10 to the 9th. It's kind of like adding and subtracting fractions when you think about it. Like if you take, you know, 1/3 plus 1/3, you add the numerators and keep the denominators. Kind of the same thing. We're going to add and subtract the coefficients, but keep the powers of 10 the same here. And you can only add and subtract fractions when you have common denominators. Kind of the same idea here. We can only add and subtract scientific notation when we have common powers of 10. Multiplying and dividing doesn't matter. Same thing with fractions. Doesn't matter what your denominators are when you multiply and divide. You can just do that. But when you're adding and subtracting, you need common denominators in fractions. You need common denominators or common powers with scientific notation. Okay, so subtracting these, I got a lot of extra zeros. If you want to, you can use your calculator to do the coefficients. We'll do this the old-fashioned way. I can't take 3 from 0, so I need to borrow. I get 7. Since I borrowed from this, but I can't go anymore, I'm going to make that a 9, but I had to borrow from this one. And I had to borrow from this one. And once again, because this was 0 and I couldn't go any farther, I got to borrow from that one. All right. Now, that wasn't 0, so we're good there. So 10 minus 3 is 7. 9 minus 7 is 2. And then we have 9, 9, 8, and 8. So we got 8.89927 times 10 to the 9th, keeping that common power, kind of like the common denominator there. All right. Let's do another one. What about negative exponents? Ooh. So let's check out 5.7 times 10 to the negative 2nd power plus 6.8 times 10 to the negative 4th power. All right. So as I mentioned before, we kind of want to match the higher exponent. And in this case, the higher exponent is negative 2. I'm back. So we want to try to make this negative 2 when it was negative 4. So if you remember, because it's a negative exponent, this means that this was a really, really small number. So we have to make it, we got to match it to the negative 2. So this was, if we think about it, the 6.8, we moved 1, 2, 3, 4 spots. So it really looks like this. We only wanted it to move 2 spots. So we got to go 2 spots. I should have taken these 2 spots away. All right, to make it 0.068. So I've got 5.7 times 10 to the negative 2nd. I should give myself a little bit more space again. And 0.00, wait a second. I gotta remember, I gotta go 2 more spots. So I need 1 0. Yep, that's right. Times 10 to the negative 2nd. All right, so once again, I want 4 spots to get here. I only wanted to go 2 spots. So 1, 2, that lines up my decimals, lines up all my place values. So now I can go ahead and add. So I got 8, 6, 7, and then 5. Keep the common powers times 10 to the negative 2nd power. One more problem to look at. And you might think, well, this looks easy because I've got similar powers of 10, so I can just add them together and be done with it. But you're going to notice there's something a little different about this one. All right, so exponents are the same. That's great. All right, we can just add the coefficients together. So I can take 4.8 and 7.9, add them together. I can keep my common powers of 10. So times 10 to the 8th. 8 plus 9 is 17. I'm going to carry this one. 4 plus 7 is 11. I still got that 1, so I got 12. And I'm not happy. All right. And hopefully you're saying right now, you're right. We're all not happy because MEP is sad because 12.7 is not in between 1 and 10. So we got to make 12.7 in between 1 and 10. So this is no different from what we did before with multiplication and division. I can think of 12.7 as 1.27 times 10 to the 1st power. So I can think of this as 1.27 times 10 to the first times 10 to the 8th, and just add these exponents. So it's 1.27 times 10 to the 9th power. Now we're happy again because we're between 1 and 10 here with 1.27.
Happy!
That's my daughter Jenna. Say hi, Jenna. All right. Another way to think about this one is because this is a positive exponent, that means we went 8 places to get here. And if we got to go one more spot, we can think of, okay, add 1 to that 8 to get the 9th power. All right, so nothing real major, but that's another option or another type of problem that you might see where you have to fix the coefficient. All right, so now what I have for you, kind of like we did scientific notation earlier when we first introduced scientific notation. There was an ALEKS assignment where there were 15 problems, and I asked you keep going and going and going until you get 100%. So any question that you miss, they're just going to give that type of question to you again until you reach 100%. So that's your goal for the rest of the day. I think I only put like 12 questions on it this time. It's not that bad. It's called Computing with Scientific Notation. And like I said, just keep going. Complete this until you get 100%. And then I'll put that in the grade book as 100%. It would be lovely for everybody to get 100% on that assignment. And like I said, sorry that I wasn't able to make it today. Hopefully I will be there tomorrow. And we've got some work to do. Good luck.